Hello everyone and welcome to another video. So today I wanted to have a quick discussion talking about parameterizing and describing surfaces. So mathematically, a surface is really nothing more than a line or a curve which has an added extra degree of freedom. So in other words, maybe the easiest way to think about this is remember with a line, all you've got is you have some independent variable x, and then you have a dependent variable, in this case let's call it y. And generally there's some function that is going to map any x value to a given y value, right? So the idea with a line or a curve is that for any given x value you pick, this function g is going to assign to it a output value y, something like this, right? And you can pick any number of locations, and this is going to give you different points. And basically a curve or a line, right, is just something that describes this entire function g, right? So the idea with a surface, right, is it's just like a line. In a line you have a single degree of freedom or a single independent variable x. And now with the surface, all we're going to do is we're going to look at what if this function g has now two independent variables, say an x and a y, and this function g then assigns a z value to that. So for example, let's draw this picture. Again, if you might now have something like this, where you now have an x and a y axis, right? And now this function g is going to take in any x and y. These are your independent variables now, and this assigns a value z for a given xy point. So you go ahead and you come down here and you say, okay, maybe I'm interested in this x location and this y location, so that gives me a point here. This is like my xy, right? And the idea now is that this function g is going to take this and assign to it a value z to it, right? So again, you do this, and now what you can see is instead of getting a single curve or a line, this function g is going to describe some kind of surface overlaying some domain in the xy plane, right? So that's the general idea with the surface. So in general, you can usually write them something like this, right? The z value is just the output of some function g of x and y. So this is what we're going to refer to as maybe like a simple surface, right? So to take an example about this, let's look at this guy right here. So here you can see we've cooked up this function g, right? So here's your g of xy, right? And you can see that for a lot of different values of x and y, particularly if x and y are sort of contained within a radius of a circle of radius a, this is basically going to be a real number, right? And what we end up with is, as long as you choose x and y sort of quote unquote intelligently within this circle, maybe I'll draw it like this, right? So here's x and y, right? As long as you choose x and y values within a circle of radius a, you'll basically get a surface overlying this. And in fact, if you look at this long enough, in fact, I'll show you a screenshot of what this looks like. This is basically just a hemisphere, right? It's half of a perfect sphere of radius a, okay? So this is an example of how you could maybe go ahead and describe a surface, right? It's just some function, and you can see this surface is fairly simple, right? Now, what's interesting about this is an alternative way that you can write this is, let's go ahead and rewrite this expression. So an alternative way to describe one of these simple surfaces is a lot of times you can write this as f of x, y, and z has got to equal some constant, okay? So in this case, you can see easily we could just rewrite this thing to basically look like, if we solve this thing for a squared, you could write this as x squared plus y squared plus z squared is equal to a squared, right? And now we are going to consider z positive, basically z greater than or equal to 0, right? So if you look at this long enough, I think you'll agree that this is basically an equivalent representation to this, okay? This is a little bit nicer. We're going to see in a second that this is a little bit more helpful for some of our downstream mathematical calculations, but theoretically they basically describe the same surface. A lot of times what this is referred to is, these are sometimes referred to as level surfaces. Let me just write that down. So these are sometimes referred to as level surfaces, because you see what happens is that as you change this alpha value for different values of alpha, you'll get different sets of x, y, and z locations which satisfy this equation. right? So you'll end up with different sets of curves or surfaces. So in our case, you can see as you change alpha, you're basically kind of changing the radius of this sphere. So for different values of alpha, you are basically describing different hemispheres of different varying radii, right? So let's see, why is this formulation a little bit helpful? Tell you what, let's go ahead and give me a second to erase the board and let's investigate this a little bit further. All right, so let's again look at this surface that's described by this level set here, okay? So again, here's our surface. This is S, and again, I've just drawn it over here in kind of a generic picture of this blue, right? It's just some surface we've got in space. Now, what I want to also consider now is, let's see what happens if you have some curve. Let's call this curve C1, and let's say it's got some parameterization as shown here, right? So again, we talked about parameterizations when we were talking about line integrals, but all we're really talking about here is, let's just draw this curve C1. So there's some curve, that's here in space. Let's make it lie on this surface. So the idea is you've got this curve C1 it's part of this surface. You can think about this, if this surface is like a blanket or something like that, maybe C1 is one of the threads that make up the blanket as it's woven in between, right? And the idea with this parameterization R is that this parameterization describes any location along this curve by a single independent variable t in this case, right? So as t changes, this vector changes, and at the tip of the vector always stays along this curve C1, right? So again, that's the picture that goes along with this. Now, like we said, we want this C1 to lie in that surface S, right? It's one of the threads of the blanket, right? So if that's true, that means this is true, right? It means that when you pass the parameterization of that curve into the function, it has to equal alpha, right? In other words, all of these x, y, and t's that are described by the parameterization of the curve, when you plug it into the function, right, you get out alpha, right? So that is what it means to have the curve C1 intersect or lie on the surface S, right? So you end up with this relationship, right? Again, nothing earth-shattering right now. Now, what's fascinating though is, let's go ahead and take the derivative of this equation down here with respect to t, right? And you can see this function f is a function of x, y, and z, and x, y, and z are functions of t. Since I want to take the derivative with respect to this sort of inner variable, I have to apply the chain rule, right? So what we end up with is, let's take the partial of the left-hand side with respect to t, and take the partial of the right-hand side with respect to t, right? The right-hand side is easy. This turns into a big fat 0, but I got to do chain rule on this guy, right? So chain rule is, this is what you get, right? You get df dx times dx dt plus df dy times dy dt plus df dz times dz dt, right? And now look at this. You can actually break this up into sort of two vectors, right? I'm going to collect all of the partials with respect to x, y, and z here. Then I'll collect all the partials with respect to t here. And now if you stare at this long enough, look at this over here. This, if you stare at this, right, I think everyone will agree, remember from our discussion on gradients, this is the gradient of the function f, right? That's one way you can interpret it. So this vector here is nothing more than gradient of f. And this guy right here, if you stare at him long enough, and you recall our discussion when we were talking about parameterizations and line integrals, this is really giving us r prime of t, right? Which really was physically, this is the derivative of how it's changing with respect to time, which we showed earlier in our earlier discussion. This is basically the tangent vector, right? So if you have this point of, of interest here, let's call this point P, okay? What we've got right here is r prime. This is the tangent vector. So what that means is, let's say this, as you increase t, this is moving like this. So the tangent vectors, maybe let me draw this in another color so we don't get confused. Let me draw it in, shoot, I probably should have done this in, yeah, let me rewrite this. Let me rewrite this as r prime of t. I'll do this in green so we can differentiate the two. R prime of t, this is the tangent vector, right? So I'm going to draw the tangent vector in green. So what ends up happening is, this is like this, right? So here is r prime of t, right? The tangent vector. So it's tangent to the curve C1, but it's in the plane, right? So it's tangent to both the curve C1 and it's tangent to the surface S, right? At this point P, right? Now, what we're saying here is if you look at this equation, right, let's rewrite it down here. You can write this as gradient of f dotted with r prime of t has to equal 0, right? Here is our fascinating result. So what this is saying right here is that this vector, gradient of f, when you dot it with the tangent vector, it better equal 0. In other words, the only way that happens is if these two vectors are perpendicular to one another, right? They have to be 90 degrees apart in some sense. So what that means is that this gradient of f, which I was drawing in red, I guess, and I just realized I've got too much red here. Sorry, let me switch colors again here. Let me change this. Instead of this being in red, let's pick another color that we can deconflict with. Let's do it in purple, okay? So let's call the gradient of f will be in purple, right? So here's gradient of f, okay? So gradient of f, it has to be 90 degrees, or it has to be perpendicular to this green vector, right? So I don't know, let's pick something, who knows? Something like this, right? Here's one potential, gradient of f, okay? Now, what's fascinating about this is let's go all the way back here, okay? And let's say instead of a curve C1, why don't we just repeat this analysis for some other arbitrary curve? So change this now to C2, right? And you can go through all of this exact same discussion, all this exact same analysis, and what we end up with is let's draw this other curve C2. So C2 is some other thread or of the blanket, right? So let me draw it here maybe as like a dashed line or something like this, right? You have some other curve C2, right? So the idea is, again, remember, C1 and C2, they both lie in the plane of this, or they lie on this surface S, right? Let's make this curve C2 also go through this exact same point P of interest, right? So if you think about this, again, we come up with the exact same analysis that, okay, there's going to be a curve or a tangent to this point in another direction here. So this is now going to be r prime of t. Okay, so what's interesting is now this actually is going to force us to realize that, you know what? The gradient of f still has to be perpendicular to the tangent. What this is basically saying at the end of the day is this vector gradient of f, it has to be perpendicular to all possible tangent vectors through this point that lie on the surface. In other words, this has to be normal to the surface at the point, right? Because the only way that this purple line is going to be perpendicular to both this first green line and this second green line. Again, remember, those two are some arbitrary threads in the blanket there. There's some, but they go through the surface S. So basically, these two lines are in the tangent plane to this surface S at the point P, right? Does that make sense? So the only way that you get a vector which is dot product with any arbitrary tangent vector is it's going to have to then be normal to the surface. So the only way that this gradient is going to work is this gradient has to either be pointing this way, right, which is normal to the surface, or I guess technically it could be pointing the other way, right? The direction doesn't matter. Both of these are going to be tangent. But what we end up with at the end of the day is then we realize that what this means is that the gradient of f is a vector that is tangent. Not tangent. That is normal. Sorry, I'm getting the terminology. I hope I didn't misspeak earlier. Is normal to S at point P, right? So this is fascinating, right? It's basically telling us that if you calculate the gradient of the vector, or of the function f, of this level set function f over here, you calculate its gradient, it is basically describing for you a normal vector, a vector that is perpendicular to the surface S at any location. So it's, again, this is a really interesting fundamental result that the gradient of f is giving us a way to easily calculate the normal vector of this surface S. So tell you what, let's look at the example back to that same hemisphere we were staring at earlier. All right, so let's go back to our hemisphere of radius A, okay? And what we want to now do is let's pick a point that we're interested in computing the surface normal at. So I've just gone ahead and picked this random point here, and it looks pretty random, but take my word for it that this actually is a location on the surface. In fact, I think it's somewhere, I don't know, let's make it up. It's, it really doesn't matter. Conceptually, it's somewhere on the surface. If you plug these numbers into this equation, it is true. So this location is on the surface somewhere. Let's call this point P, right? Okay, so now in order to get the surface normal at that point, all we need to do is compute the gradient. So let's take the derivative of this. This is the f part, right? Take that with respect to x, y, and z, and as you can see, you just get 2x, 2y, 2z, right? Now, in order to get the gradient, this tells us the gradient at any location x, y, z. We want to evaluate the gradient at that point, right? So all you need to do is plug in this number for x, this number for y, that number for z. You end up with this thing, right? So this is the gradient, or the surface normal vector at that point P. So as you can see, it's pointing in some random direction, but I guarantee you that if you were to draw this vector, if you put the tail of the vector at the point P and the tip this distance away, you would get something like this. This would be your gradient of f at point P. Right? So this is the actual surface normal vector at this location. And again, instead of me trying to butcher this drawing, let me show you a screenshot of a little movie I made where I plotted this in Mathematica, or I'm spinning it around. You can see that that magenta line is indeed the a surface normal to that vector, right? In this case, it happens to be pointing outwards, but in some situations we're going to investigate in the future, that vector might be pointing inwards into the sphere. The orientation might matter depending on your application, but we can guarantee that it is normal to the surface at that point P. All right, so while the level surface method is a great way to describe some simple surfaces, let's talk about a more general and kind of more robust way to describe more potentially complicated surfaces. So just to refresh your memory, we kind of did this already with lines. And again, remember the idea with a line, the way we parameterized an arbitrary line or an arbitrary curve in space was we said that this curve is a function of some independent variable t. And again, there's a single independent variable t. And this independent variable t, it ranges between some values, say a and b, in this sort of t space, or this t line, if you want to think about it this way, right? So what we did is we took any location here between a and b on this t line, and we developed a parameterization function r, which basically said you give it any single value along this interval between a and b, and it will tell you the x, y, z location of the curve, right, of where it's located. So you can easily see that as you start here at a, this maybe starts at one end of the curve, and as you increase t all the way up to the top level b, you can kind of use this function or this parameterization r to sketch out an entire curve in space, and this curve could do all kinds of crazy things, right? So in a similar fashion, right, we see that a curve, even though it exists in three-dimensional space, it's really a one-dimensional object in the sense that there's 1 degree of freedom, right, t. That will describe any location along this curve c, right? Now, the idea with the surface parameterization, it's just adding 1 extra degree of freedom. So now what we've got is, instead of just having a single independent variable t, let's say you now have 2. Let's say you have a u and a v. So now we're allowed to choose any locations in this UV domain over, now it's instead of just not just a single simple segment, right? But now it's a two-dimensional region in the UV plane called R, right? So we pick any location in this R, and what we want to do is develop a parameterization function. Sorry, I have capital R, and now I see I have a little r, which hopefully we're not going to conflict here. But little r is our parameterization function, where you pick any u and v pair. This function will then give you the corresponding x, y, z location of the surface. So you can easily see that as you start moving around in this UV plane, the parameterization function will then sketch out this location of the surface S in the Cartesian XYZ location, right? So again, we're just expanding. It's like basically taking the line and expanding by adding 1 additional degree of freedom, right? So what this parameterization function R is going to look like is, like we said, it's just a function where you give it x and give me a u and a v, and what that does is this function will then tell you the x, y, and z locations of it. So really, x, y, and z are functions of your parameterization variables u and v, right? And again, I just like to think about it typically as like a vector, but sometimes you'll see it written like this, where you have an x component times the unit vector plus the y component times the j unit vector plus the z component times the k unit vector. So this is just another way to describe it, and we're going to see this is a lot more robust. It's going to be able to allow us to describe more complicated functions. So let's look at an example of this. All right, so let's go revisit that same hemisphere example we were looking at earlier. So again, remember, this is, I think, the first parameterization we looked at in the very beginning of this discussion. So let's think about finding a parameterization for this by basically finding this function r as a function of u and v. And again, remember, what we need to do here is we need to be able to find a function which describes the x locations, the y locations, and the z locations. Okay, so what's helpful about this is, you know what, we already have something that describes the z, right? And now if you look at this, we can just say, why don't we choose u to be equal to x and v to be equal to y, and in that case, z is just this. So in other words, our parameterization could potentially just be something as simple as u, v, and then square root of a squared minus u squared minus v squared, right? So here's a parameterization, and now what we also have to do with our parameterization is we have to describe the region in the UV plane over which this parameterization is valid. So again, if you think about this long enough, this is basically just our circle that we saw earlier with radius a, right? So here is one potential parameterization of this function, or this surface S, which is valid, right? Now, this doesn't mean that this is the only parameterization of this surface. So in fact, let's go ahead and if you think about this long enough, this hemisphere thing, in fact, a hemisphere or a half sphere or actually a full sphere, any sphere, why are we dealing with Cartesian coordinates, right? You think about this, and a sphere would be ideal for being described using spherical coordinates, right? So we had a completely separate discussion on spherical coordinates. So if you're not familiar or comfortable with spherical coordinates, feel free to check this out first. But if you are, I think everyone will agree that spherical coordinates, it's exceedingly simple to describe this system, right? So in spherical coordinates, all we're basically saying is, let's go write this down. So you have some location in spherical coordinates. It's typically described by a radial distance r, a azimuth angle theta, and a inclination or a polar angle phi, right? So again, this is, radius, this is azimuth, and this is the inclination slash polar angle, right? Okay, so in this case, remember now the conversion between spherical coordinates and Cartesian coordinates was really simple, right? So x, well, maybe not really simple, but it's just this. It's r sine phi cosine theta, right? That's the x location. The y location looks really similar. It's r sine phi sine theta. And then the z location is just r times cosine phi. Okay, so that was the mapping, right? Now, what makes this really easy to describe is if you think about this for spherical coordinates, what we basically have to describe a sphere is that the radius r, right? This thing is just constant at the value a. Right? That's the definition of the sphere of radius a, right? And now what we want to do is we're going to let the azimuth angle run between the ranges of, say, I don't know, 0 and 2 pi, right? So that will go all the way around the sphere in one direction. And then what we also want to do is we want to let the inclination or the polar angle also vary, but let's just only do the top half, so pi over 2, right? So that's kind of what we want to have happen, okay? So we're going to let the azimuth and the inclination angles vary between these ranges, and then the radius is just constant at a, right? So in other words, if you stare at this, we can basically just say, okay, the radius is constant, right? At a, right? And now all we have to do is, if you think about it, what we're saying here is since we're going to let the azimuth and the inclination angle be free or run over these values, these are really our two independent variables in our UV plane, right? So in other words, let's go ahead and just choose, for giggles, let me see, what did I do just to be consistent? I chose u to be equal to the inclination angle, which is really, if you think about this as being a globe, this is like the latitude, right? And then we're going to choose V to be the azimuth angle, which is really like your longitude, again, if you're thinking about this as a big globe, right? Well, a big globe of radius A here, okay? So in this case, we basically just need to make all these replacements. So U is phi, so let me take out all these phi's, okay? Just replace them with U's. U, U, U. And take all the thetas and replace them with V's. V, V. That's it, right? And now this, if we put this in matrix form, right? And actually here, let me move this over to one side. I'm just going to put all of these together like this, right? This is your x as a function of u and v, y as a function of u and v, z as a function of u and v, right, is equal to this thing. So this here is our parameterization of u and v, right? And now the benefit of this particular parameterization is now when we sketch the region in the UV plane where we are interested in, look at this. We said that u is theta, so I gotta be, u is the longitude, or, no, sorry, I'm pointing at the right thing, right here, latitude, right? So that's phi, that's gonna be between 0 and pi over 2, right? And then v, which we said was theta, or the longitude, which is going to run between 0 and 2 pi. So this is like this, 2 pi. So now the region for this case is actually purely rectangular, right? So here is my region R. So again, you can see that this parameterization, it looks different, right? The region is different, but both these two parameterizations describe the exact same surface. And again, for giggles, let me just plot them over here in Mathematica just to convince you that these are the cases. So the top one is the first parameterization, and then the second one is the spherical to Cartesian kind of conversion system, right? So this is great. This helps us basically parameterize this surface in two different ways. All right, so now that we've got a good handle on how to parameterize a surface, let's revisit that idea of a surface normal. So remember earlier we looked at how if you had a level surface description of a surface, you could take its gradient and get its surface normal. Well, what if we now have a parameterized surface like we just saw? How could I potentially compute its surface normal? So again, let's go ahead and take a look at this picture. So here's the general idea, right? So again, just to refresh our memory, right? We've got some surface S, which is defined by basically first looking at a parameterization and defining a region in UV space. Let's call this region R, right? And then we are going to go ahead and pick some location in R, like, I don't know, let's pick here, right? So here's U and V, okay? And then at that point, what we have is we have this parameterization R, right, which will basically give us a location at UV, right? That gives us this little dot, okay? Now, what's interesting is let's go ahead and ask ourselves, what happens if we just change this location a little bit, right? So instead, let's maybe change, how about just change U? So maybe let me, I probably should have drawn this someplace else. Let me move this a little bit up here. Here is UV, right? What if I move like some distance like delta U? Okay, so now I'm at this point U plus delta U and V, right? So here's another location, okay? So what ends up happening now is that this vector will change a little bit, right? So maybe it goes over here, right? This one is now R of U plus delta U and V. Would everyone agree, right? And then there's a change in this vector. Maybe let's do this in another location. Like, oh, that's the same color I had earlier. Let's do it in purple here, right? Okay, so there's this change like this, right? So this is the change in the parameterization by changing just U, right? Okay, so I think what you'll see here is if you move along this location, right, you're basically carving out one of these threads of the blanket, so to speak, right? You're going on a curve that is in the surface S, right? So what you can see is that this is basically the derivative, right? So this change, this is effectively how the parameterization R is changing with respect to U, right? It's going to point in this direction, right? So what's interesting is that if you calculate the partial of r with respect to u, that's actually giving you one of the tangent vectors along the surface at any given location here, right? Does that make sense? Now, you can do the exact same thing down here. What if instead of changing u, I changed v? What if I moved up here by some delta v? So now this point is u and v plus delta v, right? So again, what ends up happening is, okay, this is going to change in some other direction, right? So this is now r of u and v plus delta v, right? So now you have this other changing direction vector, right? So this now is how has your surface or your parameterization changed by changing v. So again, by that same analysis, this direction is the same thing. It's going to be pointing in the same direction as the partial of u with respect to v, right? So in other words, the derivatives of your parameterization are giving you two tangent lines or tangent directions to the surface at any given point, right? So now, here's where we get to the interesting part is if I have two tangent lines, right, to a surface, I want to get the normal of that. All I need to do is take the cross product of these two, and what we should end up with is another vector. Let's do this in a third color, right? This vector, if this is dr du crossed with dr dv, right? Whoops, that should not have a line on top like this, right? This is going to be a normal vector to the surface, right? Because you're crossing two lines which are tangent to the surface. The only way that you have something that is perpendicular to both of these, right? That's the whole idea of the cross product, right? The cross product gives you a vector which is perpendicular to both of them, right? So the only way that happens is if this vector is normal to the plane, right? So at the end of the day, what we end up with is that, okay, a surface normal, let's call this capital N, right? This is going to be partial r with respect to u crossed partial r with respect to v. And sometimes what you'll see this written as is just r sub u crossed r sub v, right? But that's what we're basically saying. It's taking the partial derivative of u, or of the parameterization r with respect to u, partial of the parameterization with respect to v. Both of these two are vectors, so you cross product them again, you get another vector, which is now normal to the surface, right? So n is a normal vector, right? Now, the other thing that we should maybe mention right now is that this is probably not a unit vector. So let me write this down. Likely not a unit vector. So if you want a unit vector, sometimes what you'll see is, let's write this as little n bar, is going to be n divided by magnitude of n, right? You could do that to get a unit vector, a unit normal vector, okay? I just want to highlight this because a lot of times people love creating unit normal vectors, but in other formulations, for example, when we start talking about surface integrals next, you're most likely going to want this non-normalized version of it. Maybe we'll just leave that discussion there. So again, I just want to call out that one common mistake is making sure you know, do I care about the non-normalized or the normalized unit vector? All right, so let's go back to our hemisphere using the parameterization which kind of stemmed from spherical coordinates. So again, it doesn't matter where it stemmed from, we just have some parameterization of that surface, right? And it's, you know, reasonably complicated. But in order to find the surface normal, all we got to do is first, let's go ahead and take the derivative of this parameterization with respect to u first. So all I need to do is just take the partial derivative of all these terms with respect to u. This is what you end up with. And then you do the same thing with respect to v. So again, this is just boring algebra at this point in calculus, so I just went ahead and did this, and here's the results, right? Now, to get the surface normal vector at any location, all I need to do is take the cross product of this and this vector. So you do that, and you end up with, again, this ugly expression, right? Go over to Mathematica or have somebody do it for you, right? It's just a cross product. So this should describe the surface normal vector on this hemisphere at any given UV locations, right? So just for giggles, let's pick a location and see what it looks like there. So what we're going to do is we're going to choose a point in the UV plane that we're interested in. So I chose this location of 30 times pi over 180 and 235 and times pi over 180. And again, if you want to think about this as like latitude and longitude, that's totally fine, right? So here's where that location is in the UV plane. The thing that we got to remember, right, is this is a location in the UV plane, not in the XYZ space, right? This is where the region of the parameterization, right, runs between U and V. It is not a physical location in space. In order to get the physical location in XYZ space, we totally could just find these XYZ locations which correspond to this U naught and V naught by simply plugging it into our parameterization. So in other words, you take these U and V and you jam it into the parameterization here. That will give you the X naught, Y naught, and Z naught, which corresponds to that location. In other words, again, if you want to think about this from like a latitude, longitude perspective, if this was the latitude and longitude of your city of interest or whatnot, you just run it into your parameterization, and that should give you the X, Y, Z locations of where that is in space. And again, I use just an arbitrary A of 5 to get this location. So here, this is where it is, right? You can plot this, and this point should be on a surface, on the surface S, which is that hemisphere with, in this case, a radius of 5, right? But again, you don't need this step. This is just for giggles if you want to just see where that point happens to be located, okay? So what we do want to do is we want to find the surface normal at this location of apparently 30 degrees latitude, 235 degrees longitude, if you want to think about it that way. So all we got to do is just plug it in to here, right? We already computed the surface normal, which was good for any UV. So for this particular UV, you end up with this example, or these numbers, right? So apparently, again, same thing. If you want to use an A of 5, you can plug that in, and again, I'll just show you a picture of what this looks like. And again, it's nothing fancy. It looks like what we did earlier, but you can see that we are computing the surface normal of this surface just in a different fashion, right? Using the parameterization, and we end up with basically, a very similar idea. We basically get a vector where if you put the tip of the tail of the vector at this location and the tip of the vector this distance away, right, to kind of draw where it is, this is what you end up with. And again, it looks like a surface normal vector. So this is great. Tell you what, let's look at a slightly more complicated example, just so we can see what this looks like. And in fact, let's actually go do this on the computer in Mathematica. All right, so let's look at an example of a slightly more complicated parameterization. So here's this parameterization right here, which describes this surface. And let's again use a rectangular region in the UV plane here of this right here. So U is just going to go between 0 and 3 pi, and V is going to go between 0 and 2 pi. So let's go ahead and first define this parameterization here in Mathematica, and I'll go ahead and plot it just so you can see what this looks like. I'm going to use parametric plot 3D to do this. And as you can see, what this does is it creates this kind of cool kind of helix. And in fact, it's like a tube helix. So you can actually change the shape of this helix. So for example, if we just let U run over a larger range, how about 6 pi? You can see what that does is that creates more turns of the overall helix, and V has to do with how much of the full tube we make. So for example, if we only use, how about pi instead of 2 pi, you'll see what we end up with is just half of the tube, right? So again, this is kind of fascinating that you can have this interesting parameterization, and it can create these really interesting shapes in space using this parameterization. So again, this is the parameterization and the surface we're describing. Let's go ahead and compute the surface normal using the techniques we just described. So to do that, we are just going to go ahead and go and compute RU and RV, right, by taking their derivatives, and then I'll take the cross product of the two to get the normal vector. Now, notice right here, I am going to put a negative sign in front of the cross product. Again, remember, the normal vector, it can point in either the quote-unquote positive direction or the negative direction. They're both surface normals, okay? So let's go ahead and compute that right now. And we end up with, here you go, here's the analytical representation of RU, and here's the analytical representation of RV, and when you take the cross product, you get this analytical expression. So this gives us the surface normal at any arbitrary U and V location. So to plot that, let's just go ahead and draw that normal vector along with the point of interest UV, which is then mapped to a point on this surface, and then we'll draw the unit normal vector. So instead of me just keep talking about it, let me just go ahead and let me run my code, and you'll see that's all I'm doing here. I'm showing, this is the surface we created earlier, and then I'm going to go and plot in green. This is the location XYZ, which corresponds to the point of interest UV. And then what I'm going to do is I'm going to draw a magenta line, which is the arrow to represent the normal surface. And again, I'm going to make it start at the green point location and extend the distance by the normal vector. And this is what we end up with. So you can see here, let me turn on these controls so you can see how at U and V of 0, 0, that corresponds to this point way down here. And as you can see, our formulation does look like it is calculating the normal vector, right? And if we change U or V, our code should update because we already know where the surface normal is at any given location. So for example, let me crank U up. And as you can see, as U increases, we kind of work our way up the tube, so to speak. And then as V changes, we kind of go around a given location of the tube. So for example, if I go and change this, you can see, look at this. This is great, right? It's basically computing the surface normal at any given location on this surface. So this is a pretty fancy, fun little way to go ahead and compute surface normals of any given arbitrary surface as long as we have its parameterization. So this seems to work out quite nicely. All right, so there you have it, our quick discussion on parameterizing two-dimensional surfaces. We are going to now use this in our immediately following video where we're going to talk about defining surface integrals, and we're going to need this machinery that we put in place in order to effectively calculate those surface integrals. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you scroll down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos should come out every Monday, so I hope we'll be able to catch you at one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.